Jim Salisbury with Mitutoyo America Corporation, and welcome again to the Metrology Training Lab. In this episode, we're going to talk about the calibration of an outside micrometer. In past episodes, we've defined the concept of calibration, discussed the purpose of calibration, and introduced important aspects of what makes a good calibration method. In this episode, we'll apply all of those ideas to the calibration of an outside micrometer. Calibration is a search for errors, and we want to develop a calibration method that efficiently hunts down and finds any potential errors in the measuring instrument. So how do we do that best for a micrometer? Well, there's a nice American standard called ASME B89.1.13, and the calibration method that we'll be discussing is based on that standard. Calibration usually starts with checking out the proper operation of the micrometer. Is there any obvious damage to it? Does it move smoothly across its measuring range? Do you feel any play in it? Do the buttons work correctly? Does the clamp work? Once you are satisfied with the operation, then we begin the accuracy tests. Here at Mitutoyo, we recommend using a micrometer stand. A micrometer is a precision measuring instrument, and the stand helps eliminate the transfer of your body heat to the tool. The stand also makes the measurement a bit easier, which may help improve your accuracy. The first step is to clean the measuring faces. We'll put a little bit of solvent on a cloth, and we'll pinch the cloth between the measuring faces, like this. All right? Then we'll bring the measuring faces together to set our zero. For all of our measurements, we'll want to properly use the micrometer. This one includes a ratchet mechanism to control the force. We want to apply a nice, smooth, consistent force and listen for several clicks of the ratchet. The zero is so important, we'll want to check that a few times. The most important skill in calibrating micrometers is simply using the micrometer correctly. If you are having some struggles getting good results, find yourself a mic that is known to be good, grab some gauge blocks, and practice. It doesn't take too long to get the right feel. Once we have our zero set, we'll check the micrometer at the first test point. We recommend the use of gauge blocks. There really isn't anything better to use, and you need something pretty accurate, so gauge blocks make a good reference standard for calibrating micrometers. The ASME standard recommends 5 specific size gauge blocks for calibration. In inches, these sizes are the 210 block, 420, 605, 815, and 1 inch. The reason for these specific sizes is that they will force the micrometer thimble to be in different orientations for each test point. Remember that the goal of a good calibration method is to have an efficient test, and the use of these 5 test points will look for errors across the measuring range simultaneously with the rotation of the thimble. These 5 blocks are the most efficient test, but if you don't have these special sizes, you can choose to use others that achieve the same goal. The principle is what is important, not these specific sizes. If you do use different sizes, such as from a standard set of gauge blocks, you will likely find yourself needing a few extra test points. You can use any style or material gauge blocks for this calibration. I'm using rectangular ceramic blocks. We like ceramic blocks for calibrating mics due to their thermal properties. Ceramic blocks thermally expand about the same as steel, but they have a much lower thermal conductivity, which means your body heat won't affect them as much as steel blocks. And since you have to handle the blocks during calibration, this is a useful advantage. We also recommend the use of grade 0 gauge blocks. Grade 0 blocks are sufficiently accurate for micrometer calibration, so you can just use the value that's on the block, which makes the calibration more efficient. So let's clean our gauge blocks and take our first test point using the 210 block. Gauge blocks should be properly calibrated across the measuring faces, so it doesn't matter where you measure on the blocks. Some people like to measure near the ends, others in the middle. It shouldn't matter. Again, we want to use the micrometer properly and control the force as best as possible. Make sure the measuring faces are contacting the gauge blocks without trapping any air or dust between them. A proper measurement should not be too tight or too loose, but the gauge block should feel like it is in full contact. It should allow for some slight, smooth movements like this. It's common to take a few readings with the goal to ensure that you have a consistent value. This is typical practice when using a micrometer. It is not correct, however, to take a bunch of readings and report the average during the calibration. The micrometer should repeat within the specification limits for the length accuracy, and if not, then you should reject the micrometer. The reported error is the measured value minus the value of the gauge block. To be more efficient, it is often useful to not record the entire measured value, but just the observed error. This digital micrometer, in inches, has a 50 millionths resolution. And so the readings will be something like 0, plus 50, as in this case, or minus 50 millionths. In metric, the errors will be something like 0, 1, or minus 1 microns. Now, if you don't understand millionths or microns, go watch the episode of the Metrology Training Lab that covers units of measure. I'm using this data sheet that we use in some of our calibration classes, and it's just for training purposes. You can use any sort of form that you like. I'll write down the entire value in inches and the error in millionths. For this digital micrometer, the tolerance is plus or minus 50 millionths or plus or minus 1 micron in metric, which is typical for a digital micrometer. I'll now continue along with the other readings until I complete all 4 positions. The length tests are now complete. But that is not the only important test for micrometers. The flatness and parallelism of the measuring faces also needs to be checked. Historically, the flatness and parallelism was checked using an optical parallel, like this. Now, this method is a bit cumbersome and requires some special skills in reading optical fringe patterns. So, instead of checking the micrometer in this manner, the ASME B89-113 standard presents a much simpler method. The reference standard that we'll use instead of the optical flat and parallel is a small sphere, like this ball gauge here. You can also use a stylus from a coordinate measure machine if you'd like. So we're going to start by measuring in the middle of the measuring faces, and then set our 0 there. Now we're going to move the ball across the measuring faces, up and down, backwards, forwards, across the measuring faces. Any variation in the size is due to the flatness or parallelism of those two measuring faces. Then we'll report the range of those results. The maximum minus the minimum is reported as what we'll call the parallelism. In this case, I saw no range, and so the reading would be 0. Now, this method is generally not as accurate as using an optical parallel, but it's easy and efficient to do. When a calibration method is not easy to do and it is not the primary test, we often see labs skipping it. So we recommend using the ball because anybody can do it, and it's much better than not doing anything at all. We've also heard that some labs will use the optical parallel or optical flat if the test with the ball fails, because you can get a better idea of why it's failing. That seems like a pretty good idea, but we'll save using the optical parallel or flat for future episodes of the metrology training lab. So that completes this micrometer calibration. It looks like this micrometer is in tolerance. So that was the calibration of a 0 to 1 inch micrometer. Now in a 0 to 1 inch micrometer, we can bring the measuring faces together to set the 0. What about calibrating larger micrometers? A 1 to 2 inch micrometer, a 2 to 3 inch micrometer, or a 19 to 20 inch micrometer? Well, they're calibrated in a similar manner, but you need to use a reference standard. So let's cover that. Larger micrometers generally come with micrometer standards, such as this. These standards are useful for the shop floor setting of the 0 by the user, but they are not recommended for the calibration of the micrometer. Instead, you should use a gauge block. In this case, this 1 inch gauge block I'll use for this 1 to 2 inch micrometer. Now I will set my 0 using this gauge block. And then I'll proceed using the same 5 gauge blocks that I used before for the 1 to 2 inch mic. This time, however, I have the added complication of needing to ring each of these 5 blocks to the 1 inch block. It's very important to ring each of these blocks, one at a time, to the 1 inch reference, thereby eliminating any air in this 1 inch block from affecting the readings. This is particularly important as the micrometers get much larger. Let me ring these blocks together and then we'll take a reading to demonstrate the method. You would then continue with the other 4 blocks to complete the test. For the parallelism of a larger micrometer, the B89-113 standard recommends a test similar to the small ball, but instead uses the edge of a gauge block. My 0 is already set with this gauge block. Now what I'm going to do is move the gauge block up, down, in, and out to look for variation. And I'm going to measure right at the edges, like that. and like that, and then down, and then up. This time I see a minus 50 millionths reading, so the range of all my numbers would be 50 millionths, and that would be intolerance. And that's the calibration of outside micrometers. Remember, the method we just discussed comes from the American National Standard on Micrometers, ASME B89.1.13. If you don't like the method, you're always welcome to come attend the next B89 standards meeting to discuss it further. Thank you. I'm Jim Salisbury, and we'll see you next time from the Metrology Training Lab.